Hello and welcome to the Blue Waters webinar series. I'm Scott Lathrop at the National Center for Supercomputing Applications, part of the Blue Waters project. It's my pleasure today to introduce Mark Van Moor, who will talk about visualizing non-spatial data. And if you're watching the Slack channel, his colleague Rob Cisneros will be there watching the Slack channel to help answer questions during the presentation. Mark is a senior visualization programmer with NCSA in the Data Analysis and Visualization Group. With that, I'd like to turn over to Mark and thank him for his presentation today.
All right, thanks for the intro, Scott. Like you said, I'm a senior viz programmer here at NCSA. I've been here about 9 years and happy to talk today about InfoViz. So just a little overview. When I was putting this together, it was hard to decide exactly what level to aim this at. So decided maybe for the first, potentially more of these, that we'd aim at more of a beginner level InfoViz, maybe people that are new to InfoViz, or maybe you're new to InfoViz in an HPC setting for that. So I'm not going to do any deep dives on some of the graphics that we'll see later, unless some questions come over Slack or something like that, because you can really, it's really easy to go down the rabbit hole on improving some of these images and making them just perfect, stuff like that. So we're going to talk about what we mean by non-spatial data / InfoViz, how that compares to scientific visualization that you may have if you watched the Visit or ParaView webinars that we had earlier. They went into mostly scientific visualization. We'll go over some of the options that are out there for dealing with that type of data. Got a bunch of links at the end for more information and more resources to know where to look for more detail and more support for these types of things. And then one of the other things I want to kind of put together is have a common vocabulary so that people who are looking for InfoViz support or general data viz support, when you contact, say, an InfoViz person at an HPC center, you'll be on the same page as far as what you want to talk about or how to describe your data questions to each other. All right, so my background is actually originally in sci-viz and computer graphics, things like OpenGL, and it's only been within, say, the last 5 years that here at NCSA we've seen a lot more users come in that have been interested in InfoViz, and they have data of a different sort than a lot of the really high-end sci-viz packages like Visit and ParaView were originally intended for. So that kind of colors my view of the world and how I approach things. So I like to have this kind of clarity of vision of what really is the difference between sci-viz and InfoViz, and what are the different challenges that come with that. So on one end of the spectrum, we have kind of the traditional HPC users, which often work with weather simulation, computational fluid dynamics, a lot of astro and cosmological types of science going on. They usually have various types of set meshes. Sometimes the meshes may change through time, but for any given time slice, the mesh geometry is defined in space, 2D or 3D. And there's usually very specific types of scalars or vector data that's associated with either a node in the mesh or a cell in the mesh, temperature, pressure, things like that. InfoViz, on the other hand, there's usually no coordinate information with it at all, because this can be data that's pulled out of random text documents. It can be pulled out of musical notation. It can be pulled out of JSTOR articles for doing topic modeling or something like that. And so the arrangement of how things end up on the screen or in a visualization can be completely arbitrary, which is a challenge to work with. And then another thing that is maybe a little bit different than with SciViz, a lot of times we're worried about the relationships between different types of data within the data set. So maybe if you're looking at a social network, you're worried more about how different people are related in that network than the actual individuals themselves or something like that. And then I like to put this over on the side. GIS is a good example of something that's right in the middle. So GIS does have usually latitude and longitude data, or they have map data, but often they have associated with locations, they have social data, they have, you know, Twitter feed data or something like that. So it's a real mix of that. They're kind of right in the middle. And I'm not going to address GIS because that community has kind of their own solution for a lot of these things through programs like ArcGIS or different mapping programs that are out there. It's a whole nother rich topic out there. All right. So what are some of the technical challenges with this type of data that comes in? And this is usually where I start to get involved with projects here, are when people acquire this data and then what's the next step with it? How do we actually visualize it? Well, like I mentioned on the last slide, there's usually not any inherent spatial coordinates with these data sets. We have a lot of freedom to impose some sort of geometry or a layout on this data. Sometimes that's too much. Even with simple things like, well, how do you decide whether to do a bar chart or a line chart? If you go into a program like Microsoft Excel and go to their basic insert chart on the ribbon, there's like 20 different versions of charts, and which one do you pick? Does it matter? I think it does matter, but it's not always obvious through a program like that which way you should go. Another thing that comes up with InfoViz type data and non-spatial data is that's usually multidimensional. And it's dimensional, not spatially dimensional, but dimensional in the amount of variables that could be considered or attributes that could be turned into a spatial dimension. And if you look through InfoViz, the InfoViz, IEEE InfoViz conference papers, and a lot of their recommendations is as much as possible you want to reduce that to two-dimensional. That's not always an easy problem. That sometimes gets into really deep and complex statistical analysis, things like principal component analysis and other things like that, which I'm going to do a deep dive here. That would be possibly another webinar, how to do the actual reduction. Sometimes you can reduce things to 3D, but the 3D has its own problems with this type of data, because how do you navigate through that 3D space? It's much more straightforward if it is possible to reduce it to 2D, to reduce it that way. Have a lot of mixed data types. So this is something in SciViz, which is usually pretty in a standard mesh, very straightforward. Usually every single node in the mesh has the same data type. They're all floats, they're all double precision floats, or they're all integers. They all represent the same thing. That's definitely not always the case with random data. You can have a total mix of text data, different types of numbers. They can be integers or floating point. You can have continuous data, you can have categorical data, and not every entry is going to have, or not every datum is going to have every one of those attributes within that. So how do you deal with non-existent data is another issue. And then just with text itself, there's a lot of issues. There's character set issues. You can do a little plug if you already have an existing Python workflow. Hopefully you've switched to Python 3, because They handle Unicode and UTF-8 so much better. Unicode is an issue. Optical character recognition, if you're gathering data, if it's text data that was scanned in, scanning could end up giving you strings of text that look like line noise or just garbage, and how do you take those out or clean all that out? So a lot of issues that don't come up with kind of standard traditional meshes for, say, fluid dynamics. All right. There's also, beyond the technical challenges, there's design challenges, and I was kind of started to talk about this a little bit when I was talking about all the different options you have, even in a office program like Excel, is how do you decide, okay, once you've decided to do a line graph or some other type of chart, is it actually pulling out the information or highlighting the information that you want to communicate to other viewers of that chart? Or does it just look cool? Especially with network graphs, I think it's very easy to make something that looks really cool, but is just as confusing as looking at a spreadsheet of raw numbers. So that's an important thing. And then aesthetics do matter. We're moving into a 2D realm. If it looks horrible, you're not going to get second looks at your data from people outside your group. And we can learn a lot from the graphic design community about how to organize things to simplify what we're presenting and to clarify and to highlight all of the things that we actually want to bring out for the data. I'll talk a little bit about that later. All right. So this is something I love to bring up, and I know that Dr. Vitria Bird also had this slide in her presentation because it's a great slide to have. This is from Benjamin Fry, who I think was originally out of the MIT Media Lab, and he wrote a book called Visualizing Data. I have that in the references at the end of the slideshow. It's an O'Reilly book. If you can grab a hold of it, it's a great thing to just kind of flip through and look at all sorts of ways to visualize all sorts of different types of data. However, Fry goes through this thing he likes to call the 7 stages of visualizing data. And I'm going to go through most of these kind of slide by slide and how you can apply them to working with unstructured InfoVis type of data, non-spatial data. And I would want to point out that for me, as a programmer, the best use of this is it helps me organize my code. How do I modularize my code so that I can attack a problem coming from a new HPC community, say social sciences? They don't have maybe a well-defined or well-developed visualization workflow, especially in an HPC context. How do I start putting things together to get them to that point to where they can start visualizing their data? And I like to refer back to this and kind of chunk up my programs, modularize my programs and scripts so that they kind of fit this pattern as well. And then this is an example of the types of horrible visualization you can do in PowerPoint itself. These arrows, the dark blue arrows are meant to represent the kind of standard flow, and then the lighter blue arrows are meant to represent, just kind of as an illustration, hey, you know what, you don't have to stick to this, you can flip back and forth between filtering and mining, and we'll talk about exactly what those are later, or parsing. I know from experience that parsing is something that almost has a loop around itself many times. So it's not like kind of a hard and set. I don't want to be dogmatic about this, but it's an interesting thing. I will not have much to say about the acquire step because usually that is left up to the PI. I'm not involved with that at all, other than how do I get access to it on whatever machine so I can start looking at it. All right, so parsing. You also see this referred to as pre-processing in a lot of literature that's out there. Absolute best case is the data that's handed to me maps directly to some type of representation. That's relatively rare, but it happens occasionally. But also, don't be constrained by that. Just because something happens to be in, say, an XML format that maps really easily to some type of tree data structure doesn't mean that you are restricted to visualizing it as a tree or as a hierarchy. There may be other ways to pull out data and end up doing other visualizations for that way. Something that's relatively common, I've seen this also on the SciViz side, is that the output format may not be optimal for viz. So it may be a large data set that was chunked, cut up into slices in a particular way in order to be efficiently analyzed on an HPC resource. A lot of times that data set may not make sense for viz tools. Viz tools usually are going to work with a restricted amount or a lesser amount often of the data. I'll get into what I mean about that later. And so sometimes you want to go through and just kind of glean out important subsets of the data for that. Drawback to that is if somebody is wanting to build or is hoping for a visualization system that also allows users to interactively query data and alter the visualization based on those queries. If the data's been cleaned or filtered some way, they may not be able to do all those types of interesting queries. And as much as possible, I recommend that people use existing file formats that are out there. This isn't always possible. I do have worked with groups in the past where for various reasons they've had to create their own file format, but as much as possible I would highly recommend that you do something by tables. I mean comma separated values or tab separated values, something like that, some sort of delimited regular format, XML, JSON, anything like that is going to make life easier for everyone involved. So some parsing tools. This is actually also the reason why we're not doing a live demo. I started to look at this and I was like, this is a lot of times where I spend most of my actual work is figuring out how to parse the data. And usually when I get involved, it's because the data doesn't fit into one of these nice tools that is up there. And so a lot of custom scripting has to be done. And I didn't feel like that was appropriate and kind of an intro talk to go into. But I do want to point out that there is a lot of stuff that's out there and it's constantly improving. There's a lot of activity in this area to improve data ingestion as the whole kind of data science explosion is going on. If your data is anything like a table, CVS or anything like that, delimited records, and you have access to something like Tableau, then the importer can probably figure out how to bring it in. You may have to play around with, there's usually lots of options for setting exactly what the delimiter is. May have multiple delimiters. Text may be set off through quotations or something like that. But Tableau in particular can do an amazing job with ingesting data for that. Doesn't clean your data if there's garbage in there, like say OCR errors or something like that. But it can put those all in a separate category or something. Python, if you have a Python workflow, the CSV module is fantastic. I highly recommend that regardless of what language you're using, Python, Java, whatever, go out and use one of the modules that's available. It is actually relatively straightforward to write your own parser in Python or Perl that'll look at a basic CSV file and ingest it and do whatever you want with it. But once you start getting into, say, mixed character sets or text that's delimited or not delimited, then that starts to get to be kind of a tedious time sink to make sure that all the I's are dotted and the T's are crossed for that type of programming. There's modules out there, might as well use them. There's also this kind of new, and it's a whole family of modules in the R ecosystem called Tidy Text. I have a link here to this. They have a ton of packages. They have packages for parsing and organizing freeform text data. They also have some graphics tools that are really handy. It's really amazing. So if you have an R, you probably already know about this, but if you're new to InfoVis and are still kind of evaluating tools, I would really recommend looking at the R Tidy Text family. And then there's also, if you have on your team experienced Unix command line programmers, there's a ton of Unix command line tools. My only recommendation, and it took me a project to learn this, is it's so easy. You can find on Stack Overflow and other places all sorts of one-liners for whipping through a text file and changing delimiters from comma to tab or whatever you want to do. Capture those in a shell script because you don't want to realize that you've gone back to the same Stack Overflow page 20 times to, wait, how do I do that instead? Or something like that. Just kind of a handy thing that I had to learn how to do myself. And there's also, again, Python. I don't want to just keep pointing out Python. These are also exist in Perl and even Lua have XML and JSON modules. If they're available, please use those. There's such a time saver for that. Okay, so I want to kind of change pace for a little bit and talk about an example of parsing on a real-world project that I worked with. And this was actually led by professor here at U of I, Dr. Ruby Mendenhall, who's in sociology and is doing some really interesting work. And she used a program called comparative text mining, which I have a reference to at the end. And the output of this is it's a really interesting output. So it's kind of two parallel hierarchies. There's like one hierarchy that does a very broad overview, and you can cut that up into an arbitrary number of chunks. And then there's another hierarchy that does very focused slices of the data, and you can cut those into arbitrary numbers of chunks. So you kind of have two different is how I ended up thinking of it, two different parallel trees that were going on at the same time for that. The original Viz app that I made did all of this at once. I did not modularize correctly, and so it would take forever to start up. By forever, I mean like 2 minutes, which is an eternity to wait for if you just want to get in there and start clicking on things and exploring the data. So I realized, every time this loads, it's doing the exact same thing. Why don't I pre-process that, which I did, and turn it into XML. So I did this with Python. I don't remember exactly. There's multiple XML modules out there. They all pretty much do the same thing. For that, went through, opened up that original CTM output file, figured out what the tree structure was, and then just wrote it out in XML. I went directly through the API, the application programmer interface of the module, so I didn't really have to write that much custom code for the XML side of it. So now, when the Viz app loaded this up, it also used an XML reading library, much faster than anything I would have been able to write. Also gave it the ability to load only one of those tree branches or the other, because those were uniquely identified within the XML. And it also mapped directly to a tree data structure underneath the hood. And so that immediately set it up for whatever visual representation we wanted to do. And we looked at various things, and I'll talk about some of that later. But at this point, once you have it into a data structure, you can go for a tree map or a tree, hierarchical tree, or whatever ends up being the best thing based on feedback from your user for that. All right, so kind of getting back to Fry's cut up of the InfoViz or data visualization pipeline, filtering. So I like to think of this as the way I distinguish filter and the step after this, mining, is let's say we're looking for the needle in the haystack, right? Filtering is let's make the haystack as small as possible. Move out all the irrelevant data. So let's say we have 2 haystacks. We know the needle's only in one of them. Might as well clean that out. And we can do the same thing when we're loading up data for our visualization. The data that you're going to be able to visualize is often much smaller than the full set of data. And there's lots of reasons for that. One is if you're trying to do something interactive, you have to be able to get the data to fit in either RAM or, in best case scenario, the video RAM on the GPU. That may be quite a bit smaller than the actual size on disk. So one way to think about this is every bit of data that is actually not going to be drawn, is not going to influence the drawing, don't even load it. So this is kind of an interesting thing that's available with file formats that have metadata associated with them. Is sometimes in some of the programs that we'll talk about later, they have options when you load those files to only load certain attributes out of the file. So, for example, in ParaView, if you have a file format that supports metadata, before you click apply to actually tell ParaView to go and ingest the data, there's a checklist where you can go through and say, okay, only load these 3 attributes or something like that. And that can tremendously reduce the amount of actual RAM that's going to be used for that. So I would look for those types of options for that. And then another thing to kind of think about is even with an 8K resolution monitor, that's only 33 some megapixels, so 33 million pixels. If you have 1 billion data points, which is not that uncommon in HPC context, there's no way you can draw all of them without them overlapping and occluding each other. So unless you have access to something like a huge video wall, like they have down at TAC, you're going to have to deal with culling it out just because it's not going to fit in the resolution that you have. And if you're dealing with something that's going to end up on a laptop, and this is something I've run into, I have a relatively large 30-inch monitor and have started doing things by default in HD 1080 just so I can see them on my monitor. If I hand that off to somebody with an older laptop that can only support, say, 720p or even less, it's just not going to look great for that. So something to be aware of there. All right, mining, as distinguished from filtering, is let's say we have some character of the data that's inside the haystack, the needle. Is there something about the needle that we can highlight or bring out so that it makes it easier to find? Well, needles are metal, so we could use a metal detector or something like that. They're shiny, we can shine a light on them. That's the same kind of thing we're trying to do in the mining step here. If we are dealing with some sort of attribute, let's say it's social data, and we don't have necessarily their latitude and longitudes, but maybe we know what state they're in, and we want to highlight people from Ohio, well then pull out the Ohio stuff. Make use of the data that you have to be able to highlight the things that are important to you. This also helps with, even if you do draw a huge amount of data on a screen, say 1 million network node points or something like that in a social network, if you can highlight the ones you're interested in, they'll jump out. And the visual perception will kind of put the highlighted things in the forefront and let the other things drop into the background and let people focus for that. So that's really what we're trying to do with this mining step. And this is where stats really come in that can help. identify different characteristics that you might want to pull out. So maximum, minimum, average values, you can use all of those as ways to guide how things are going to be represented and highlighted in the actual visualization. Okay, I promise we're going to get to some actual slides of some visualization examples in just a second. All right. And then representation. This is kind of maybe what many people are thinking of when they actually think about visualization, is how do we actually draw it? How do we decide on what we're going to actually present to our viewing audience? I have a link here to an interesting flowchart from Brian Suda, who's a designer in England, who comes more from maybe a business intelligence background or a graphic design background, but has an interesting flowchart on how do you actually decide when to use a bar chart versus a line chart versus a scatter plot or something like that. Another great resource out there, Nathan Yao, who runs flowingdata.com, has a couple of books out that are really nice. They're popular level books, not academic level books. So they're really easy to kind of dive into and see some guides on, oh, if you have categorical data, maybe you should consider these, or if you have continuous data, maybe you should consider something more like a line chart or something like that. Really interesting to go for that. So I just have kind of some basic, very, very basic tips down here. And when I actually go to these, we can talk more about why one would be chosen over the other. Standard charts, kind of the things you might see in Tableau or Excel or something like that. Scatter chart, bar, line, histogram, things like that. Those are great for showing stats, for showing distributions, for showing how continual variables relate to each other, or how categorical variables relate to each other if they have kind of a relatively arbitrary or user-defined relation. Or I guess that's why you're doing the visualization, so you can discover if they have that type of relationship. Network graphs. These are great if you have an explicit relationship within the data itself. So social network relationships, or I've even seen this used for programming code libraries, how different libraries within a large coding project relate to each other. But they can be careful with these, I believe, because they clutter very quickly. They can get kind of difficult to navigate through. And then if you have data that happens to be in a hierarchical format, and it makes sense to look at hierarchically, then trees and tree maps are some options for that. All right, scatter plot. This is the go-to plot. This is where I almost always start if I have two variables or can reduce to two variables that can be plotted against each other. And they're just saying, hey, one variable goes one variable goes in X, the other variable goes in Y, and let's see what they look like. And you can actually do these for combinations of continuous and categorical. So canonically, you do this for two continuous variables. But in a library like, say, R's ggplot2, there are actually, they call them different names, but there are ways you can do a scatter plot that is, one is continuous and the other is categorical. They might call it something like a jitter plot. But those are just kind of names, and those names are going to change based on which library you're using. They're all scatter plots. That's how I think of them. And this also gave me an opportunity here to show Anscombe's quartet, which is kind of an interesting aside of why do we visualize anyway and not just look at statistics. And this was developed by Anscombe in 1973. This paper is available on JSTOR. If you have access to JSTOR, it's really short. It's like 4 pages, and it's a really interesting paper to read. He came up with these 4 different data sets. We plot them. It's obviously that they look different. right? You've got the one in the upper left, kind of linear, but with a little bit of random variation. Another one that has the kind of parabolic, inverse parabolic relationship. One that's mostly linear. Is that outlier a actual outlier, or is it possibly a data cleaning issue? We don't know, but it jumps right out there. And so when we plot these, it's pretty obvious. However, if you were to do a statistical analysis on these all look incredibly similar. They all have the same average X. They all have the same average Y. They all would have the same linear regression. They all have the same Pearson's correlation coefficients. And if you read the paper, he lists about 6 more things that they all have in common. And this is only to, like, say, 2 or 3 decimal points. But, you know, for most things that are going to round to 2 or 3 decimal points anyway, that's a lot. So this is kind of why we plot, and scatter plot very effectively shows the difference between all 4 of these, among all 4 of these. All right, so kind of the next option that's out there, this is often what you're going to see for a mix of categorical and continuous, or categorical that has counts, are the bar chart and the histogram. On the background one, which is the white with the red bars, reddish bars, this was pulled actually out of ParaView, and I'll talk more about how ParaView and Visit handle InfoViz towards the end. This was a scientific data set, and there's a built-in histogram filter that goes through and decides, user gets to set number of bins or the size of the bins that they want. Let's categorize our continuous variable into these different bins. So this happened to be density, X-ray diffraction density, I believe, at various levels. And we can see clearly here that the vast majority of data in this data set, the X-ray density happens to be in that first bin. The bin, or the chart on the upper right came out of a topic modeling project. This was one where, so topic modeling is a text analysis methodology, and one of the things that produces a ton of data, one of the types of data it will produce are things called topic lists, which are groups of words that are associated with each other throughout the corpus that has been modeled. And if you just look at the list of words, you might come up with one interpretation. But there's different weightings or different numbers or counts that each one of these terms will appear within a particular topic. And sometimes it's nice to see how that actually is distributed. So you can say, well, this is definitely, no, it's impossible to read these at this resolution. But in general, the main idea is that the topics there's 2 topics or 2 terms in the topic at the very top that are very heavy, and then there's kind of a mid-range, and then there's a gradual die-off. And that helped the scientist that was working with this data in their interpretation of what was going on, what was the topic modeler telling them this topic was about, or suggesting that this topic was about. And then another one that can be done with continuous versus continuous data is the line graph. So this might be the kind of the next step up from a scatter plot if you have continuous data in both axes. And this is Champaign County elevation profile going from south to north. The elevation is in meters, and I believe also the x-axis. This is something that I should have done and would do on a deep dive if we did more in depth on how to actually do the mechanics of this. Should always have your axes clearly labeled and what your units are, just to help viewers know what's going on. Anybody who's been to Champaign knows that this is a bald-faced lie of what Champaign County actually looks like. It looks more like this, right? Flat as a pancake. So that's one of the issues with plotting things like line graphs and scatter plots, is what is the correct aspect ratio for stretching out our data and displaying it? A lot of it depends on the context, especially if the variables on each axis have different units. And in that case, Cleveland in '94 came up with this idea. He might have come up with it before then, but the book that talks about it is from '94, is go through your data, figure out all your delta y's, and use those delta y's to change your delta x's so that the average slope between any 2 points is 45 degrees. That's called banking to 45 degrees. In the context of Champaign County, I think that would still be kind of generous to the topography of Champaign County, but it's an interesting thing to think about. One of the drawbacks to that is you get these long, skinny images like I have here. Okay, this fits on the slide because I resized it, but it's possible you could end up with something that really would stretch out over many sheets of paper or over many slides. And William Cleveland's solution to that would be to kind of split it up into maybe 6 different stacked versions of the image, where you'd have to realize, okay, once I get to the end of one image, I'm going to curl around and go back to the other one. But Edward Tufte, who's a known name in InfoViz and DataViz, his solution to that is something called sparklines, which is to miniaturize it. And you start to see sparklines in a lot of places. If you go to, say, like Yahoo Finance or something like that, where they'll have lots of financial history data or Dow Jones history data, and they'll have like 20 of those stacked right next to each other, and they have almost, maybe a criticism of it is sometimes they're almost too small to see, or at least somebody who needs bifocals like myself, it's kind of hard to see for that. But it is one option of how to handle the complexity or the issue of, if we do a proper aspect ratio to show the data, we end up with these real narrow, skinny images for that. And this is something, once I read Cleveland and started looking around, you see all the time in popular media images where somebody has made a line graph, and they have made a very dramatic line graph because they have squished it so that the slope looks exponential, but if you actually look at the units, it's not exponential, it's still linear. So that, how to do line graphs correctly, is a total deep dive. I'm not even mentioning cases where you might want to have, if you have exponential growth in your data, might want to do log or semi-log graphs as well. Okay, so then the next 3 slides are kind of all related. They're all going to use the same data and showing how they can be drawn differently and what is effective and what is not effective. Sometimes you don't know, or I didn't know until I got in there and did something, came back to the scientists looked at it, it's like, yeah, this is okay, but it's missing a feature, say, of usability that I need. So for example, this is data that came out of Mallet. This was, again, Dr. Ruby Mendenhall's project. And she was curious about how various topics related to each other based on documents that they had, or that they scored highly in. And so able to do some statistical correlation and come up with, well, these topics, say topic 82 is related to topic 97 based on a large number of documents, and so we draw a thicker edge connecting them versus we do some of the other topics. And this is a good first pass, I guess. And the problem with this, especially in an interactive context, is that a lot of networks are drawn with what's called a force-directed algorithm, and they have a little bit of randomization in them, and they also are mobile. They can move around. Users can completely change the arrangement, and if you're trying to compare interpretations over multiple people, you're not always looking at exactly the same thing, especially if somebody has gone through and clicked on one of the topics with the mouse and dragged it out of the way or something like that. And even trying to find stuff can be difficult. Okay, it's easy to find the big topics here. Topic 82, largest one, but sometimes large topics aren't actually all that interesting. They maybe are getting something that just happens to be in common through all your documents, and that's not actually the needle in the haystack you're looking for. So this was perhaps mapped to the wrong attribute. So kind of another approach is to do kind of a heat map or an adjacency matrix. And this is a grid of the topics one by one. And so you can compare topics through this. I didn't label this because this ended up being a non-starter. The only virtue this has is that topic 55 is always in the same spot. It's in the 55th column or 55th row. So if you're working with a team and you're trying to refer to things remotely with each other through email, you know exactly where to look. The only place I can think of where I've seen this effectively used is if you look in old road atlases. In the back, they will have mileage between different cities, and it's actually in this type of format often. Though instead of color-coded, they'll have numbers in there, but it's really actually the same thing in my viewpoint. And so what we ended up doing for this project was come up with something that was kind of a mix of, it was still a network, but the location of the nodes were fixed. And there's a lot of different ways you can do this. We ended up picking a radial network. So now, again, we still have topic 1, the node representing topic node, is always in the same location. We know where to find it. We can click on it. We can still see the relationships through the nodes by the thickness of the lines, though sometimes that can take a lot of tweaking to get that balance just right. And then this also afforded us the ability to interactively show what the actual topic lists are on the other side of the visualization. For that, this is impossible, of course, to read here, and even in the slide, it's a little difficult, though somewhat legible. But essentially what's going on is that now the researcher was able to interactively move through this network, select different topics, and see different topic word lists, and be able to, that would aid the interpretation of what these topics actually meant. And so actually the real lesson out of this was this is going to be an iterative process with InfoVis between the people doing the visualization and people actually doing the interpretation. Even if that's all contained within one person yourself, there's going to be a time delay sometimes between when you have an idea and when you actually get to implement the idea, and your perspective may have totally changed on that. And I have a link here at the bottom to, this is kind of, I should have maybe a horizontal rule between here. This is not related to this, but this is a great link. This is run by Manuel Lima, who was at Microsoft Research at one time. I think he's at Code Academy now. And it's just a gallery of all sorts of collections of different network visualizations. Everything from social network data to financial data to reimagined subway maps, and it's really interesting for inspiration purposes. All right, and then just for completeness, another thing that can often come up with trees, and often if you want to draw something as an actual tree with nodes and branches, you're going to end up using possibly the same software you would use for network graphs. However, there is another way to look at tree data, and that is with a tree map. Excuse me. And actually, excuse me, one of the kind of easiest ways to jump into this there's a lot of tools that are out there that will analyze your hard drive and display your hard drive contents in a tree map format. I'm not sure if Windows has this built in now, but I think Ubuntu does. If you go to the disk analyzer, it has an option for a tree map view, and you can see where are the files that are hogging up all your hard drive space, things like that. The idea is that at each kind of level within it, the size of whatever node in your tree is going to have a rectangle spaced proportionally to that size. And then a lot of these are also interactive. So if you have, say this was hard drive data and you wanted to zoom into a file and see what the subfolders, how those take up space inside of it, you'd be able to double click on it and go inside of it. One of the things that's difficult with this, and is kind of related to the random force-directed layout for a network graph, is that there's also some level of randomization in how this is going to split. You can delete one file, and the entire tree map will redraw itself. That can be a problem, and there's ways around that. There are things called Voronoi tree maps that try to deal with that. Danielle Fisher, who is at Microsoft Research, really explores this kind of idea with the concept called stability. When you're comparing visualizations, trying to give the user something to hold on to, so that when they flip back and forth, they know where they're looking at. And this is something that not every tree map algorithm is able to do, so it's something to be aware of. Now for something completely different, parallel coordinates. This is the one thing I'm going to touch on with multidimensional data. Sometimes you just can't reduce the data to get the picture that you want out of the data. And parallel coordinates is one solution to this. This is each vertical axis is a different data. This is baseball data I got from MajorLeagueBaseball.com, MLB.com. Showing different hitters. For that, I'm not a huge baseball fan, but I know what some of these are. If you're not a huge baseball fan, don't worry about it. The idea is the same, whether this was other types of data, is that we have these separate axes, and now instead of having a point in a scatter plot, we have a polygonal line segment. This green highlighted segment is one player. And so the interpretation is not exactly the same as where you have a scatter plot. You can look at that one location in space and, hey, that's my datum. Now we are forced with having to kind of see how this looks at over the entire range of all of the axes. And there's lots of, you can do a deep dive on this as well. There's lots of things going on here. Some of these axes are continuous, slugging percentage, and average, those are continuous variables. Things like stolen bases and strikeouts, though, are categorical, or actually maybe counting would be a better way to put those. And so what is the proper way to scale the axes between axes that are categorical and then continuous, and then different levels of continuous? So this is getting into baseball a little too much, but it turns out that batting average goes from 0 to 1,000, though realistically nobody's going to hit above 400. But slugging has some weird upper limit, like 1.43 or something like that, because it's not normalized. And so normalization may become a matter. And then directionality of the axes may become an issue as well. For example, strikeouts are a bad thing. So I had to flip the strikeout axis so that it went from a low at the top to high at the bottom, as opposed to the default, which was the other way for that. So I think these are a very interesting visualization, but they do take, I believe, some practice or some getting familiar with to really pull some things out. All right. So this is, I feel like I'm volunteering for a series of webinars. inadvertently, this is another thing where you could do a definite deep dive on, and that is, okay, we have parallel coordinates, we have bar charts that are the default in ParaView or Visit. How do we make them more effective, and how do we make them more appealing and get a message across? This is where graphic design can really come in to play, and where UI principles come in, especially when you do something interactive with that, with your data. And the main thing that I think is important is our brain and our visual system, fairly consistency across populations, interprets data that's coming in from the world, the photons that are actually hitting the back of our eyeballs, in a relatively uniform way. And because of how this whole mechanism of visual perception happens, certain things get processed in the eye itself, certain things get processed in the visual cortex, and certain things get processed in the whole gestalt of the brain. And we can leverage these things to make certain things pop out. And this is kind of the hierarchy of which things get processed first. Position gets noticed well before actual shape does. McKinley talks about this. If you get a chance to leaf through Colin Ware's information visualization books, they're fantastic. They go into all of this, have lots of examples, and tremendous bibliography of where to, if you want to do a deep dive on how visual perception actually works for that. General, most important rule of thumb, though, that I've seen when looking at my own viz and other people's viz is tone down the colors. Got a link to Color Brewer, which is, I want to say Joanna Brewer, web tool for setting up color maps. And I believe even a lot of tools now like Visit has a bunch of built-in Color Brewer generated color maps that are great to use, especially for categorical data for that. All right, so some examples of what these mean when we talk about the visual hierarchy and which things are going to jump out for that. And these are meant to be read in the same kind of order as on the previous slide. So starting at the top row and going from left to right, position is going to jump out at people way more than area. Even subtle position changes are going to jump out more than subtle area changes. So there's obviously a huge gap here in the middle of the position, but there's little subtle things between, oh, hey, we can just make out that this bar is jumped out from the collection of bars. And these little variations in distance between the lines as we go in various parts that jump out immediately compared to if we go all the way down to shape. Boy, it can be hard to track, okay, where's the shape that has two curves on the same size? And if you're setting something up and expecting a casual viewer to look at a visualization and have to remember that, oh, a curve on the upper left corner means something different than a curve on the lower right corner, it's probably going to be difficult, I think, unless they're willing to spend time there learning what your mapping actually is, to really dive into your data for that. So these are all things that you can pull into, and some of these things just immediately fall out of the type of plot. Scatter plot, for example, immediately falls out position. You know, if you're looking for what the maximum of my data is, that's immediately going to show up in a scatter plot. Same with a line plot. Though there are issues with density with scatter plot, whether or not you're actually looking for dense areas or are you still looking for something else, then that's where you want to mix in another visual cue. So maybe you also want to add color to highlight some other data attribute or something like that. And the lesson for that, going back to the piece of advice before the color brewer link is that muted colors can afford increased info density. This is actually an example I saw Edward Tufte talk a couple of years ago here on campus. And the example he brought up, and I thought it was great, was Google Maps. Think about how toned down the colors are in Google Maps, and yet how much information is there. There's so much information there. Really a fantastic use of, or an example of how toning down colors can really help actually increase the amount of information that's able to be displayed. That has to do with a visual perception thing sometimes called dazzling, which if there's too many bright colors next to each other, it is almost like a Bridget Riley op art piece from the 60s. It can be very hard to look at for that. I'm not going to spend too much time on this. Interaction, my main piece of advice for interaction is if there's a GUI library available or built into your system, or you're evaluating systems and you have a choice between looking at something that has built-in GUI library, go that direction. I made the mistake when I first got into InfoViz. I did a lot of things with processing, which I still love for totally free-form InfoViz. But if it gets to the point where somebody wants to have sliders and buttons and interactive axes, then it's too tedious to write all those yourself. So definitely find a library out there that supports that. And then one thing that didn't occur to me until I actually got into the nitty-gritty of programming this is what we're really doing with a lot of interaction on a programming side is we have to take a mouse coordinate, we got to map it back into the underlying data structure, which may or may not be the same as the visualization data structure, to find the data that the person clicked on. That may or may not be trivial, depending on how things are set up, and it may have a significant runtime cost. So this is maybe too much computer science, but if you're doing a graph data structure underneath the hood, depending on how your graph data structure is set up, searching through it may be a linear process, or it may be a constant time process. And so that can have implications on what exactly how you want to structure your data down the road. All right, so I'm going to wrap up with just some links where people can do some deep dives on this. This is not meant to be comprehensive, but there's a lot of things that I've used personally and that I've evaluated, so take that for what it's worth. If you're starting from scratch, you're new to HPC, you're new to InfoViz, you have data that will fit on your local resource, it's relatively clean, or you can jam it into a table format somehow, highly recommend looking at Tableau. I think the main drawback to Tableau is the licensing. If you're at an educational institution, they may have an educational license for that, which would make that possible. There is a publicly available version of Tableau. It's called Tableau Public or Tableau Cloud. The drawback to that, last time I looked, was you have to upload your data to the cloud. So you don't want to send research data up there, certainly. But if you just want to evaluate it, it's a nice way to evaluate it. You're starting from scratch, data is a little messy. Again, I'm going to recommend the R ecosystem, especially the tidy text. This has really exploded in the last few years, and there's a really good, strong movement behind it. Open source, and that R graphics cookbook is an online, it's kind of like a preprint to the O'Reilly book of the same name. And is essentially the same as the published version. Really great resource for quickly getting into R in graphics. If you need web interactivity, that's kind of a specialist case. There is a very popular JavaScript library out there called D3. D3 itself, not maybe as low level as something like processing as far as when you want to add in things like axes and buttons and interactivity. But there are, I would consider, if you do need that type of functionality, looking at something like Bright Charts, which is still D3, but has gone in and built a lot of automatic charting libraries for doing line charts, bar charts, but also user interaction. So you don't have to do quite the deep dive you do into doing something from scratch in D3. There's a thing called Vega, which is out of the IDL, which is at University of Washington, which is one of the top academic schools doing InfoVis research. They have also their own kind of, I wouldn't say it's a competitor to D3, but it's an alternative. It's also web-based, based on JavaScript and CSS. Cascading style sheets, ways of laying out data, very interesting project. And then Google Charts right off the bat, kind of similar to Excel, but it does allow you to do some interactive web things. If you already have a Python workflow, there's PyPlot, Matplotlib available for that. They have lots of great resources on the web for those. Now, if you do want total freedom in what you're doing, you want to completely blue sky your viz metaphors, you're working with people who have programming and graphic design background, or maybe want to get into that, then processing, I think, is still a fun option. There are a lot of, but it's totally freeform. You're starting from scratch at the level of draw a pixel here and make it this color. Maybe not quite that bad. They do have functions for lines and ellipses and things like that, but it's pretty low level. Though not as low level as OpenGL. And then if you're on HPC resource, you have people on your team, or you yourself are a C++ programmer, you have some familiarity maybe with the visualization toolkit, Viz pipeline model, which is one of the standard scientific visualization packages that's out there. They do have an InfoVis pipeline and set of filters and contexts that are out there. There's a great YouTube video that I've linked here that goes over that. I think it's about an hour, but it's definitely aimed at people that are already familiar with VTK and C++. But it is an option if you fall in that category. And then general networks, there's a lot of options out there. I have Gephi first, but that's kind of maybe in an indeterminate state of support right now. It's run basically by two people in France, I think, and I think originally it was a grad school project. I'm not sure exactly what's going on with that right now, but it's still available to download and to play with is interesting. Cytoscape comes out of the bioinformatics and genetics community. Very powerful. I can do some amazing viz with it, but I find that its user interface takes some time to get used to. And GraphViz. If you have absolutely huge networks, you do actually want to plot networks with millions of nodes in them. You're not worried about interactivity. GraphViz, which I think was originally from IBM or sponsored by IBM, or maybe even Data General or somebody like that, is the way to go. And it is not interactive. You write a file that describes your network, so you have to know how your network is laid out, and then you can proceed from there. Okay, and then I want to spend a slide talking about, since we are at NCSA and we have Blue Waters, what's going on with doing any of this stuff on Blue Waters. So the big viz tools on Blue Waters are ParaView and Visit. We also have IDL, but we kind of recommend that that's only run for kind of quick and dirty data analysis on the head nodes. But on the compute nodes, we have ParaView and Visit. They definitely support doing visual analytics and InfoVis on scientific data, traditional HPC scientific data. So if you have a mesh and you want to do a histogram on it, Perfectly possible to do that in both ParaView and Visit. Where they're less strong is in pulling in completely random, unstructured data and doing an entire InfoViz workflow. ParaView kind of has a project that's working on that. I'm not sure what the state of that is. There hasn't been any traffic on it on the ParaView mailing list for a while. I'm not sure what the state of Visit is in that regards either. But they do both have a large number of filters, plots, operators. I just have them listed here just as kind of an example of what things are available. If you have side viz data that you want to do some analytics on, what you can do built in with that. And then IDL, I don't do much IDL myself, but when I do, I almost always have forgotten it, and I go to a refresher. This IDL Coyote, who I think is a relatively well-known figure in the IDL community, has all sorts of tutorials and references on how to do various types of plots in IDL. All right, references, you're supposed to end with the most exciting slide that you have, so I'm not sure if I'm doing that here. It kind of depends on what your bent is towards that. I want to point out at the bottom, any of Edward Tufte's books are interesting just to kind of flip through, and they're very insightful on what makes an effective visualization. Flowing Data, which is run by Nathan Yao, mainly run by Nathan Yao, has a ton of information on it as well. Mainly focused on, say, business intelligence or data that you might see on New York Times and their infographics. Not HPC level stuff, but it's still, I think, worthwhile at least looking at and seeing what's going on. All right, so I think that's all I have for today. Would love to hear feedback, please. I know Scott's probably going to ask you to do a survey. Please fill out the survey. And if you have feedback on, hey, this was great, but we'd love a deeper dive on some other aspect, I'd love to hear that type of feedback, because this was a very broad and general overview. So thank you.
Well, thank you very much, Mark. It's clearly a very broad topic with lots of options and capabilities. I have to admit, I enjoyed Tufte's books many years ago, and it's good to see there's still a valuable, appropriate reference. With that, then we'll switch to the final slide. I'd like to, if you have questions, go ahead and post them on the Slack channel. We'll go ahead and take them and monitor them and get you responses as soon as we can here. But thank you, Mark, for a great presentation. Our next upcoming webinars, next Wednesday, June 14th, by Peter Kaysen on Copernicus, a workflow tool. And then June 21st, Jeff Sale from the San Diego Center will be talking about hyperglyphs for the next visualization webinar. And we'll just take a moment. I don't see any more questions being posted, so we'll say thank you, Mark, and thank you all for joining us, and we'll see you again in the next webinar. Bye-bye.